Hey, good morning, everyone. So today is May 11th, and it's a very special day for me because it's the birthday of one of my scientific heroes since I was a little kid, Richard Feynman. In his honor, I'm going to deliver this talk on galaxies. I'm preparing this for a public viewing session tonight. I'm going to make this available on my YouTube channel, and I welcome comments and suggestions. So I'm certainly not an expert by any means. So if you find any um, errors or historical inaccuracies, please let me know. The reason I'm interested in this story about galaxies is because it is tied up very closely with some of the deepest questions which human beings have pondered. Where are we? What's our position in space? For a long time, we thought the Earth was the center, and that's no longer true. Are we in the center of the Milky Way? How big is the universe? Is the Milky Way the entire universe, or is there something outside the universe? How did the universe evolve? What is its age? What is its mass? And ultimately, what is its fate? So these are some of the questions I would like to touch as I narrate this story about galaxies. Right. The story begins with the Milky Way. It is certainly one of the most prominent structures which human beings have been seeing since the beginning of time in the night sky. Imagine the caveman looking at the sky and just wondering, what is this structure? What is it made up of? And so many questions were unanswered for them. And when there was no answer to the questions, they came up with their own answers through fantasy, imagination, right? So that is mythology. Every single civilization of humankind, without exception, came up with their own version of what the Milky Way is. The ancient Indians said it was Akash Ganga, the river of the heaven. Now, just like rivers on earth, there are rivers in the heaven, and this is just a river. And then Native Americans and Africans came up with other versions of the Milky Way. They said it's like the path taken by the sacred animals or the campfires of our ancestors and so on. I think the most popular one is by the Greeks, who said it was actually milk spilled by some goddess or something. Now, you have so many options on the tables. Which one are you going to pick? Which one is correct? So this is where Carl Sagan said it very well. Well, when you have many different stories to explain something, all of which are based on belief, faith, without any evidence, the most plausible explanation is maybe they're all incorrect. Well, certainly they all can be correct. Well, if they all can be correct, maybe the most possible scenario is that they're all incorrect, right? And how do we seek the truth when we have uncertainty, right? And this is where the scientific method is going to come in. So this is a method which scientists use to explain the physical world, to understand the physical world. It's a mode of thinking which starts with observations, collecting data, right? And then you try to understand the data that we have, and there will be lots of questions that are going to come up, and you identify a problem or two that you want to dig deep. So that's when you research. You look up the literature, see what's already done, what is known, and then you develop your own theory, your own hypothesis, right? Based on the data you have, based on the literature that you have studied, you develop your hypothesis. So this is a new hypothesis, and people are not going to accept it immediately. It needs to be tested, right? Everything should be subject to rigorous testing, and that is where you design an experiment to test your hypothesis, okay? Where you bring in various control variables and just test your hypothesis. And finally, you get all the results of your experiment, you analyze them, and then you draw your conclusions. If your conclusions align with your hypothesis, well and good, you have made some progress. Otherwise, you go back to the drawing board and tweak all the dials and knobs and go through the whole song and dance again. So the scientific method is a beautiful, powerful, elegant method which uses mathematics, logic, and an iterative process. It was pioneered by the Italian scientist Galileo Galilei, arguably the father of modern science, who uh, gave the first scientific explanation of the Milky Way back in 1610. That's 1609, 1610. That was the famous year where he turned his telescope to the night sky and he pretty much grabbed all the low-hanging fruits, like craters of the moon, and rings of Saturn, moons of Jupiter, phases of Venus, whatnot. And he also observed the Milky Way and what appears to be like a cloud arching across the sky is actually made up of individual stars. So that is the first scientific explanation of the Milky Way. But then people wanted to know more. And okay, what's the architecture of the Milky Way? And here you have a picture of the famous William Herschel and his sister, Carolyn. So they both worked on a number of things together. And here's a replica of a telescope they built. And they observed the Milky Way and different sections of the Milky Way and counted the number of sections in stars in each section. And they were able to come up with a rough map of the Milky Way. And this is the Herschel's map of the Milky Way back in 1785. Right? And as you can see, he placed the sun more or less at the center. Okay. Although this is not accurate, I would say it's pretty impressive for the technology that they had at the time. It's just like a basic ground-based telescope that he built himself. Right? Quite impressive. And then if you want to know exactly where you are in the Milky Way, you have to measure distances in the universe. How do you measure distances in the universe? And that's a very hard problem, you see. Right now in this room, I know I'm not in the center of this room because I know I'm closer to this wall, but farther from that wall. My binocular vision gives me a depth perspective, and I can tell that I'm closer to this wall and farther from that wall. That's why I'm not in the center. But this one is not going to work at a cosmological, astronomical scale. You need other methods. And people use the parallax to measure distances to nearby stars. So this was first done in 1838, although this idea was known to the ancient Greek, including Hipparchus. The first successful measurement of stars which are so far away was done by Bessel, 1838. So the idea is that you measure the position of a star, nearby star, relative to background star at a given point in time, let's say in January, and wait for 6 months later when the Earth is on the other side in its orbit around the sun, and then examine the same star again, and you'll see that it appears to have shifted its position. And you can measure the angular shift in position, and that along with the known diameter of the Earth's orbit, which is twice the astronomical unit, simple trigonometry then reveals the distance to the star. A simple idea, and that is how people were able to find the distances to nearby stars. But what about stars which are much farther away? A new technique must be developed because the parallax method was not working. So before I tell you this new method, I want to say a few words about the universality principle, because that is the principle that played an important role in lots of other calculations, including the distance calculation. The universality principle is the following simple law, which states that all parts of the universe are subject to the same laws that we find here on Earth. So what a great thing to have, right? So imagine if that was not the case, it would be a terrible nightmare for scientists to figure out what's going on in the universe. I mean, can you imagine a universe where gravity satisfies inverse square law in this galaxy and an inverse fourth law, an Andromeda galaxy, and I don't know, inverse 10th law in the Pinwheel galaxy or something. That would be terrible. But that's not the case, fortunately, because the laws are uniform across the board for all parts of the universe. Right? So here are some famous examples. The first one was pioneered by Isaac Newton. The planets, stars, everything in the universe obey the same Newtonian law of gravity as do falling apples or paths of projectile. Okay. And another thing which came up a little later, I think this in the 19th century, people observed that the light from distant stars reveal the same atomic physics that we observe here in our labs. So this universality principle is quite instrumental, in the progress of science. And this was applied by Henrietta Leavitt, who was a computer back in the day at Harvard College Observatory. And she came up with a new technique for measuring the distances in the universe. And looking back on it, it was an important milestone in our journey. And looking back on it, she actually deserved a Nobel Prize for her work, although she died relatively young and for which she failed to receive the prize. So she was a computer back in the day. By that, we mean she's a person who was hired to do some cataloging, calculations, a lot of clerical work, but very important work, right? And they were not paid much, in modern currency, that's like about $10 an hour or something. And she pioneered a technique which allowed astronomers to go much farther than nearby stars. What she was doing, she was actually looking at stars in the small and large Magellanic clouds, and the stars that she was looking are Cepheid variables, right? So lots of terms. Let me explain. What are these clouds? So the small and large Magellanic clouds, if you go to the southern hemisphere, you'll be able to find them. So in my trip to the southern hemisphere, I was able to, New Zealand, I was able to see this. So here are the clouds, the irregular dwarf galaxies. And she was looking at stars within that galaxy. And there, she observed what are called Cepheid variables, which are bright stars, which are variable stars. They pulsate radially with a fixed period, typically less than 50 days or so, right? So they expand and then shrink, expand and shrink. It's not quite a sine curve because they expand rapidly and then shrink more gradually. So that is the behavior of Cepheids. And when she collected lots of data, thousands of stars in these clouds, and then she plotted the data of the period versus the absolute brightness, she found the graphs of this form. Now, anyone who has taken some basic class on functions like algebra 1, algebra 2, these quickly realize that, oh, that's a logarithmic graph. So therefore, she said, okay, I'm going to scale the variables and see what's going on. And then she got straight lines. So all the data points fell along a straight line. So that means there is some linear relationship between the absolute brightness. Well, actually, she was looking at apparent brightness, but she knew this could translate to absolute brightness because all these stars were in the same cloud. So direct correlation was observed between the brightness and the period. And that is the Cepheids stars that she was looking at. And this is now we call the Leavitt's law. But this needs to be calibrated. Just knowing a linear relationship is not enough. What exactly are the coefficients of the linear relationship? So she was hoping that somebody is going to compute the actual brightness of some star inside the distance to the cloud, because once she knows the distance, then based on the apparent brightness, she can calculate the absolute brightness. Okay, and then you'll get this law. And therefore, this led to what is called the 5-step method to compute the distance to any nebula. First, you find a Cepheid in that nebula. And right there, we're using the universality principle. Cepheids must behave same everywhere. So if they have one behavior in the cloud, the Magellanic clouds, they should have the same behavior everywhere, because the evolution of formation of star cycles is same in all parts of the universe, right? So find a Cepheid, look at its period, and Leavitt's law can be used to find the luminosity. Okay? And once you have the luminosity, you look at the star, you know how bright it is. That's the apparent brightness. And the inverse square law gives you the true distance. And this is the inverse square law, how the apparent brightness diminishes with distance. So it's inversely proportional to the square of the distance. If you double the distance, the brightness drops by a factor of 4th. If you triple the distance, brightness drops by a factor of 1/9. So that was the idea. To observe anything, all you need is Cepheids and their periods, which can be computed. So this was like a quantum leap in our understanding of distances in cosmos. The first man to apply this successfully was Harold Shapley, who was actually at the time head of the observatory in Harvard College Observatory, shortly toward the end of the tenure of Leavitt. He was working on something called globular clusters. So these are stars, thousands, hundreds of thousands of stars, which are gravitationally bound. And so this one, the picture that I got, is one is of Omega Centauri. And he was looking at these clusters, and he used Leavitt's technique to find the distance to each of these clusters, right? And he found something interesting. In each of the clusters, he was able to find Cepheids. And then using the 5-step method, he found the distance to this Cepheid. And what he found was that the sun is not at the center of these globular clusters. And therefore, he made this bold hypothesis. The point on which the system of globular clusters, I think he observed like 90 clusters or so. The center of these globular clusters is also the center of the Milky Way. So this is how science evolves. You should be able to make this bold move, and then people will come and test, and hopefully you're correct, and that's how you can make advances, right? If he just tabulated the distances and he left it there, that's okay, but that's not good enough. So from there, you make up a hypothesis, because I want to find the center of the Milky Way. Are we the center? He said, no, we are not the center. And he found that the sun is actually away from the center. The center is far from the sun. It's towards the constellation of Sagittarius, right? And that's the center of the Milky Way. So here's a picture. The sun is over here. We are somewhere here, far from the galactic center of the Milky Way. So, and later people used space telescopes and other advanced techniques to actually prove that Shapley was indeed right. And that is why astronomers sometimes refer to him as the 20th century Copernicus, right? Nicholas Copernicus, back in the 15th century, told us that the Earth is not the center of the solar system, right? It's the sun that's the center. But Shapley told us even the sun is not the center of the Milky Way, it's off the center. And then he also made another conjecture based on the distances he calculated. He conjectured that the Milky Way is the entire universe, right? He calculated the size of the Milky Way, and he got a figure of 300,000 light years, right? Distance traveled by light at a staggering 3 times 10 to the power 8 meters per second for 3,000 years, right? That's the size that he estimated. And he said, that's it. After that, it's void. There's nothing. Now, how do you test that hypothesis, right? And for a very, very long time, this is what people believed. The Milky Way was the entire universe, right? In fact, for the classical astronomers in the 17th century, 18th century, everything that's not a point light was thrown into one basket, lumped into what's called nebula, right? Even when Messier made up his catalog, Today we call this, okay, this is Andromeda Galaxy, this is Pinwheel Galaxy, M31, whatever. But back in the day, he didn't know that he was looking at galaxies because galaxies were not known, right? Everybody thought it's just the Milky Way. So we come a long way, and that's the story I'm telling you. So the Shapley's conjecture is that the Milky Way is the entire galaxy, right? Around the same time, another gentleman, astronomer, actually quite well known, more famous than Shapley, is Herbert Curtis, who formulated that a different hypothesis based on his study of the Andromeda Nebula. And keep in mind, we're not using the word Andromeda Galaxy, right? So galaxies were not known yet. So it's still early 20th century, right? And he observed 4 brief novae. Novae are spontaneous brightening of point stars, right? So like it appears something popped up in sky out of nowhere. Tycho Brahe first observed this, and Herbert Curtis observed more in the Andromeda Nebula. And he noted that they were 10 times fainter than anything observed before. Then he said, like, again, using the universality principle, he said, okay, if all the nebulas should be more or less the same, follow the same principle, why should these be much fainter than what we observe in our Milky Way, right? And he said, the only reason is that they're actually, they only appear to be fainter only because they're much farther away. So, and then he calculated, he did the math, and he said, this nebula must be 500,000 light years to Andromeda. He got an estimate of 500,000 light years to Andromeda. So if these stars were 10 times fainter when compared to the brightness of the novae that we observe in Milky Way, the inverse square law told him it's 500,000. He said, oh, that's too far from anything inside of Milky Way. And then he came up with his conjecture. There's a lot more going on in the universe outside the Milky Way. The Milky Way is not the whole of the universe. Being a mathematician, I used a set theoretic notation there. And he called them island universe. So they're universes in their own right, much like our Milky Way. So that's the great debate, one of the most famous debates in astronomy that held in 1920 at the Washington, D.C. Smithsonian Museum. So on the left, you have Shapley, who was claiming that the Milky Way is the entire universe. And on the right, you have Curtis, who's saying that, no, there is a lot more going on outside the Milky Way. The universe is much, much bigger than the Milky Way, right? In particular, the debate was surrounding this, was centered on this spiral nebula in the constellation of Andromeda. So the Andromeda Nebula. So is that a cloud of gas and dust within our Milky Way or a distant galaxy? Like from our perspective, when you're seeing it, how can you tell whether that's within the Milky Way or outside the Milky Way? So it was a whole day long meeting, and several astronomers gathered. They both gave their own presentations, and there was some discussion and debate. But really nothing came out of that debate right away because both had their own models, and they have their own ways to reason and support. What's needed is that we needed more data, okay? So now I have to switch gears and explain a little bit about spectroscopy, which is coming from understanding the electromagnetic waves which are emanated by stars. The light that we normally perceive from the sun is the visible light, which is a small band of a much broader spectrum of light. And this was first discovered by William Herschel, almost by accident. William Herschel and serendipity, these two go well together. Like how he accidentally discovered a new planet from his backyard, right? Uranus. And similarly, he was trying to understand if there is any relationship between temperature, and color of, when you go out in the sun, you feel the warmth, right? But then Newton famously split the sunlight into the spectrum, right? The 7 colors or whatever. But then he thought, okay, let me put my thermometer on each of these regions and see if it's recorded the same thing. And to his surprise, there was some variation, but then he also wanted to make sure there's some control in the experiment. He said, okay, let me move my thermometer outside the spectrum and I should record room temperature. And when he moved outside the red end of the spectrum into the infrared, well, actually it's not called infrared back then, but outside the red, to his surprise, it got even hotter. And that means there is something else going on there, which we don't just see it, we feel it. So that was an indirect detection of the infrared, and later people expanded that into other areas, microwave and radio waves, which are longer wavelengths, and shorter wavelengths or higher frequency on the other extreme. What's incredible is that these stars, which emit these starlights, when you pass them through a spectroscope, you get the fingerprint. So this is the absorption spectrum of the stars. These lines are like really fingerprint. So you can use those lines to tell what chemicals are there, what chemicals are missing, and you can also tell whether they're coming towards us or moving away from us. If they're moving away from us, the lines will be shifted to the red end of the spectrum, right? And you can also measure their receding speeds and all that stuff. And this work was done by Besto Slipher. So 1912. It's kind of unfortunate that this man did lots of great work, but unfortunately, based on my reading, this gentleman, he didn't get the recognition that he deserved. Anyway, that was his work. And around the same time, there were developments happening on purely theoretical astronomy. And this is Albert Einstein, man who needs no introduction, right? He formulated his general theory of relativity, which superseded the Newtonian theory of gravity, which was able to explain the anomaly in the orbit of the Mercury, among other things, which was famously verified during total solar eclipse a few years after. So, and one of the predictions of Einstein's theory of relativity is that the universe is expanding. Okay, there's a lot going on there. So in the interest of time, I'm just compressing that, right? Initially, Einstein didn't believe that. He believed in a static universe, eternal universe. And in fact, he thought it was collapsing. So therefore, he tweaked this equation to throw in a cosmological constant so that it would be stable. Okay, but then other people corrected the math and they showed that the universe will be expanding based on the Newtonian theory, based on Einstein's field equations. Universe is expanding. So no, that is where matter stood, right? And lots of things going on. 1917 also, there was a famous telescope being built, 100-inch Hooker telescope at Mount Wilson, California, right? It's the world's biggest telescope, which can peer into the depths of space. Okay, now this is a very, very, very exciting moment. We're coming to the climax here of the Great Debate. So we call the Great Debate. So we have two gentlemen, Shapley and Curtis. Shapley claimed that Milky Way is the universe. Curtis said the universe is much bigger than the Milky Way. Okay, and around the same time, we have all these developments in spectroscopy and modern telescopes and theoretical results from Einstein's theory of relativity. All these things were there. And it was a very, very exciting time to be in astronomy. That's when Edwin Hubble enters the scene. He graduated from University of Chicago with degrees in mathematics and astronomy. And he was able to put all the pieces of the puzzle to resolve the Great Debate. So see what he had at his disposal. He had the access to the 100-inch telescope. He was working at Mount Wilson Observatory, and he was well aware of the Cepheid variables, and he was able to use the telescope to get lots and lots of data of Cepheid variables in the Andromeda Nebula, and he used the Henrietta's technique to measure their distances, and he used Schleifer's work to measure their redshifts, to see their recessional velocities, and he had Einstein's general theta relativity. So based on all that information that he had, he was able to effectively compute the distance to the Andromeda Nebula. And the distance he came up with was 1 million light years away. Okay, so in astronomy, you keep hearing these big numbers, right? What exactly is 1 million light years away? So it's very hard for the human mind to fathom such large distances, right, at the cosmological scale. So this is about 6 quadrillion miles, or 6 times 10 to the power of 18 miles. It's a mind-boggling distance, right? And when Edwin Hubble was presented at I think it was the Royal Astronomical Society, there was a standing ovation. No man in human history was able to scale a distance of that order before. So it completely changed the game. And it provided the first compelling and conclusive evidence that Andromeda is its own island universe. That's it, end of the story. There's a lot more outside the Milky Way. In fact, there are more and more galaxies later found using this technique. And today we have Webb's deep field images. Here is the one that I got. Everything where you don't see a diffraction star pattern here, everything else is a galaxy. In the observable universe alone, we now know that there are about 100 billion galaxies, just like our Milky Way. Okay, the great debate is done, but here's a scorecard just to put things in perspective. The great debate is about whether the universe is the Milky Way or not. Well, it's not the Milky Way. The Milky Way is not the universe, right? Shapley got this wrong, Curtis got it right. But there are other parts in their theories. If you look at them, Shapley correctly figured out that the Earth is not the center. So he got correct for that. But Curtis said that the Earth was the center, and he was wrong there. And what about the true size of the Milky Way? Neither of them got it correct, because the truth is somewhere in between what Shapley estimated and what Curtis estimated. The true size of the Milky Way is about 100,000 light years across. So let's not throw the baby out with the bathwater. Even though Shapley lost the debate, sort of, but there are some elements that we get from we know from his work, ingenious work, that the Earth is not the center of the Milky Way. And now you might ask, okay, why did Hubble become so famous when he was really standing on the shoulders of the giants and putting all these pieces of puzzles together? Well, that was already quite formidable. But then Edwin Hubble went much further. Through his work, we also know very well that we live in an expanding universe. And not only that, we know the rate of expansion. All galaxies are receding away from us at a rate directly proportional to their distance from us. So everything, the space is stretching, right? It was actually predicted by Einstein's theory of relativity, but here we have empirical evidence based on direct observation. Once again, understanding how the scientific method is working, right? And the analogy that's often given here is that imagine you are trying to bake some, I don't know, cake or something. You put some dough with some, I don't know, raisins or something, and you put it in the oven. Once it bakes, everything is going to spread out, and the distances between individual raisins is going to spread out, right? It's going to extend. That's what's happening. All the galaxies that we look out, they're red shifted, right? So that means they're moving away from us because of these waves. They're getting stretched, and they're moving onto the red side of the spectrum. So here you see the farther the galaxy, the more distant are the lines from the base spectrum lab reference. And the constant of proportionality. So the galaxy that's much farther is going away much faster, right? And the constant of proportionality is the Hubble's constant, right? It's a very, very, very important constant in astronomy. And this number fluctuated throughout history for the last 100 years, and right now the most widely accepted constant is about 70 kilometers per second per megaparsec. So because the speed was measured in kilometers per second and distances are measured in megaparsecs, Okay. Anyway, don't forget, don't worry too much about the units there. Now, quite incredible is that this Hubble's constant allows us to compute the age of the observable universe, right? We see in popular media reports 13.7 billion years, right? And how did that come out? Well, the universe is expanding. What if we run the clock backwards? So then it should be contracting. So at the very, very early universe, everything was all together. And then there was an explosion called Big Bang, right? So the Hubble's work led to the Big Bang theory. And assuming that this rate of expansion is constant, which one can discuss, the Hubble's constant is 70, we can actually get a ballpark estimate for the age of the universe. And there's a simple calculation. Distance traveled is speed multiplied by time. Easy. Everybody knows that. Therefore, time is distance over the velocity. But what did Hubble estimate? The rate at which a velocity is saying goodbye to us is proportional to how far away it is from us. So V is h naught times d. Now, whenever you have two different equations, both important equations, and you combine them, magic is about to happen. So if you substitute this equation for V in the equation for time, you get time is, well, the d's cancel, you get 1 over h naught. So the age of the universe is just the reciprocal of the Hubble's constant. So it's 1 over 70. Now you can grab your calculator, punch in 1 over 70, and do all the unit conversions, convert seconds into years, and speed of light into kilometers, and so on. You get 13.7. Incredible, right? And that's not the end of the story. In more recent years, this is one of the biggest breakthroughs in the 21st century. People now observe that the universe is not only expanding, but it's actually accelerating, right? And three gentlemen here shared the 2011 Nobel Prize in physics for coming up with this breakthrough. Okay. Finally, there is one troublemaker. As always, we resolve some things in science, and that opens a can of worms. Okay. One of this famous mathematician, Andrew Wiles, explained research. What is research? Research is like entering a dark mansion that you have never been before. It's all dark, and you're trying to find a light switch. You're constantly bumping into the furniture, and you spend a long time there, about 6 months or so, trying to find a light switch, and you turn it on, it's all illuminated, and you know exactly where you are, and it's beautiful. Oh, that's where I was running into a problem. Oh, the fridge is here, and you see everything. And then you enter another dark mansion and spend another 6 months trying to find a light switch. Okay, after the problem is solved about the great debate, there were other things of our theories of cosmology which were not adding with observations, right? So we want one theory which explains everything. If it explains some things and it doesn't explain something, then you know that your theory is not perfect. It needs to be tweaked. So there was this problem of galaxy rotation, which was an annoying problem because things were not adding up. Based on Newtonian, Einstein work, whatever, the rotation speed of the galaxy, so all these elliptical galaxies, they spin, we know that the speed at which a star should be spinning, okay, kind of should follow a path like this based on the models. Well, it should increase and then it should decrease and plateau. This is what you would expect. But what's observed is this curve, not the yellow, but the fluorescent curve, right? So that means that some things are not adding up. So all these stars, these galaxies, they're behaving as if there's a lot more mass than what we actually see. Okay, so then scientists hypothesize, just like Einstein tweaked this model. Instead of I'm going to throw in a cosmological constant to explain this, people say, okay, there's something called dark matter, which we don't see, but it's there. It's like a halo of force or matter, whatever you want to call that. Nobody have any clue about what it is, right? It's affecting, it's tugging on this galaxy, which is speeding it up, But only time will tell whether this is true or false. But my colleague Matt Kaplan at ISU thinks that this is real. But anyway, that's far beyond the scope of my knowledge. I'm going to end there, but let me summarize what we learned from this presentation. Number one, the sun is not the center of the Milky Way galaxy. Loud and clear from Shapley's work. The Milky Way is not the only galaxy. This is we get from the work of Edwin Hubble and others. The Andromeda galaxy is far outside our galaxies, and now we know there are tons and tons of galaxies outside the Milky Way. We live in an expanding universe based on Edwin Hubble's work again, which is giving evidence to the Big Bang theory. And in more recent times, we learned that the universe is not only expanding, but it's accelerating. And last but not the least, I hope this talk showcases the power of the scientific method along with the universality principle, which scientists have been using in their ongoing exploration of the cosmos. Yeah, maybe I will end with this quote of Stephen Hawking, who said that we are an average breed of monkeys on a minor planet of a very average star, right? If you had end the quote right there, that would be somewhat pessimistic, but there was a happy ending to that. But yet we can understand the universe, and that makes us something very special. So here are some references. So my favorite book on the science of astronomy is The Big Bang. So if you want to learn about Great Debate, there is a chapter on that. It's called The Great Debate. You can look into that. And then there is this free open source book on astronomy. Chapters 25 and 26 talk about galaxies. Morrison and Wolf. And there's a YouTube channel by Dr. Becky. It's very good, your friendly neighborhood astrophysicist. And I have another favorite book by Julian Schwinger, which he shared the Nobel Prize with Richard Feynman, actually, on Einstein's legacy. Thank you. And you can get my slides by scanning your phone. And if you have any questions, put them in the chat. I will look at them and I'll get back to you. Thank you.